And then, yeah.
Okay, great.
I do not.
So I'll start now.
Yeah, you can start. And again, I'll say that if people can switch on the videos, it is preferred if you do.
Okay, great. Firstly, I think I'll start with thanks, Rohan, for inviting me to give this talk. Like, it's a pleasure talking to OMC. Like, I went through your website, and it's super fascinating what you people are doing. So, continue reaching heights, and yeah. So what I plan to do today is give a small exposition on what is called measure theory. So this has recently grown into interests and has its applications in all areas, right? From number theory to core physics, and it's all over the place. So we'll take a small problem and start working on it. So we won't go through all the works in physics or number theory, but rather we'll just take a small problem of how you can assign lengths to certain subsets of R. So and we'll study some properties of whatever results they give out. Right? And just a remark out here I can start off with is that I have no intention to complete all of what I have planned. So just stop me for any questions at any time. So all I want is that whatever I say, it should sit deep in your head. That's my major goal for today. And so one thing I should mention about this is that it's highly interconnected. So if I say something at the very start, there may be places where I'll have to use it at the very end. So it would be nice if at any point, if it's not making sense, just stop me then and there and don't wait for doubts. Okay. And so I'll just give you a brief overview of what we're going to do today. So we'll start with integration. So we'll take integration as the motivating factor for why we need to define length. And we'll see that talking about integration will naturally give us the necessity of, say, building upon this notion of length. So then we'll extensively talk about this notion of length, and we'll touch upon all sorts of things like which sets can be measured, which sets can't be measured. And we'll end by constructing a set that cannot be measured. So that's the agenda for today. So let's start at a seemingly unrelated point. Oh, and before that, if my handwriting gets too undecipherable, just stop me and let me know. Let's start at a rather weird point. So imagine you have 100 different coins of, say, 4 denominations: a 1 rupee coin, a 2 rupee coin, a 5 rupee coin, and a 10 rupee coin. You have 100 of these coins, not each, but you have a total of 100 coins which are scattered across the floor. And what are some possible ways in which we can find the total amount in the room? So we'll start at this point and see how we can build upon. Okay. So this is a rather too much of a trivial question to answer. So I think I'll just go ahead with answering, and I'll wait for some responses in the questions where you have to actually think. So one possible strategy would be to simply pick up coins and count them one by one until all the coins on your floor are exhausted. Right. That's one natural method. What is another method? Another method is you take the nearby coins and you pile them up into heaps, right? So what I mean is, if you have, say, some coins here, you pile these coins into a heap, you pile these coins into a heap, and you pile these coins into a heap. Now, then you count how much is the value in each heap. Say this heap gives 7 rupees, this heap gives, say, 11 rupees, and this heap gives, say, 3 rupees, right? And then you add the total in each heap, and you get the total. I can't do addition. 21, I hope. So what is another strategy which can use? This is the second strategy which you can use. Another strategy which you can use is you pile the coins based on denominations, right? You stack up all the 1 rupee coins, and then you stack up all the 2 rupee coins, then all the 5s and all the 10s. And what you need to do is count the number of 1 rupee coins multiplied by 1, count the number of 2 rupee coins multiplied by 2, and so on, and add the values which you get after multiplying. That will give you the total amount in the room, correct? Now we'll see how this guy translates into integration of real valued functions defined on R. So that's what we're going to do today. So I'll just use okay. So consider a function from a comma b to R, which is continuous. I don't intend to write everything, so some parts I'll be saying, and some parts this iPad is just for giving you a picture of what is going on. Okay. So let f from a to b to R be a continuous function. Okay. Now what we intend to do is to find the area under this graph. Oh, can you see my screen, Rohan?
Yes, it's perfectly clear.
Okay, great. Saptarshi, should I wait or? Okay, I think, or maybe just try rejoining back if you can't. Okay, so if you have a continuous function from closed a comma b to r, so this is how somehow what the graph looks, and your goal is to estimate the area under the curve. So what you want to be able to find is this total area, right? The way I drew it should kind of give you a hint. So what I'm getting into is what is called Riemann integration. Okay, so since I see quite a few first years here, this is something which you will see in your very end of your analysis one course. So you better pay attention now. Okay, so if you have the closed interval a comma b and a function defined on it, what you do is you try to approximate this area using rectangles. Rectangles are one of the easiest objects to measure the area of, right? So this is an idea which you would have seen in your 12th grade also. Right. So what you do is you split this interval, the domain of the function, into different pieces, right? So you split it into, let's call A as t naught and let's call B as tn. Okay. So you split AB as ti and ti minus 1 to ti, right? I equals, let's say, 1 to n. Okay. Now what you do is you just take a look at f restricted to this ti comma ti minus 1. Okay, now here f attains a minima somewhere, correct? Here let's say f attains a minima somewhere here and it attains a maxima somewhere here, correct? So you do it for all such partitions, right? You do it for all such intervals. So let's say we do it for this part. Here f attains its minima here and its maxima here, right? So similarly, if I go to the very end, f attains its minima here and its maxima here. Okay, so a nice approximation of this area would be to find the area of all these minimas first. I'll do it over all these partitions. So this area is going to be less than or equal to the integral of the curve, right? And this red area is going to be greater than or equal to the actual integral of the function, right? And this is precisely what we'll try to formalize, right? Now, a thing which you can notice is that if you increase the number of partitions, that is, as you increase your number n, so then your approximation gets better and better, right? This is something which you can convince yourself with. And our goal for the next 5 minutes is to formalize whatever I said now. Okay, so what we'll start with is a partition. A partition, remember, is simply you're cutting this closed interval a comma b into pieces, right? So you'll start with this partition. You call a to be t naught, and you take a number t1 which is greater than t naught, and you take t2 and you go all the way up to tn minus 1 which is less than tn, which you call it b, right? So this is what you call your partition, which I denote p, right? And what do I need to measure? To measure the area of, let's say, this blue rectangle, what do I need? I need the length of each partition, correct? So that is precisely what I define now. I call delta ti to be ti minus 1. Okay, so that's just the base of the rectangle. And for the height of the rectangle, what I'll do is I'll just take a random point, right? Now, that is one thing which I can do. Or in other words, what I can do is, how did I define the blue rectangle? The blue rectangle, I simply took the minimum value of the function when my function's domain was restricted to this particular interval, correct? So what I'll do is I'll define a value small mi, which is just going to be my infimum. If you're not familiar with infimum, just think of it as minimum. Okay, I'll take my infimum value of f of x as x is in this interval ti minus 1 and ti. Okay, and similarly for the red rectangle, that is the big one, I'll take the maximum value of f it attains in this interval, right? So the formal term for that is supremum. Okay, supremum and maximum are slightly different, but it's okay for now. If you're not comfortable, you can stick with maximum. Wherever I write infimum, you can read it as minimum, and supremum you can read it as maximum. Okay, as x is in this interval ti minus 1 to ti. Okay, so this is one basic notation. Now, what is my approximation to this area under the curve? The area under the curve, what I need to find is firstly the sum of areas of all these blue rectangles, correct? So what's the area of the first blue rectangle? The first blue rectangle is t1 minus t naught, times it's what I called small m1, correct? And the second rectangle is small m2 times t2 minus t0. And I'll keep adding all of this, and I'll get my total area under the curve as an approximation, right? So, and this is precisely what I define now. So I'll define what is called a lower sum. Lower sum, again, this corresponds to the blue rectangles. So the lower sum with respect to the partition and the function. So both of these are going to depend on the lower sum is going to depend on both, right? It depends on how I choose my partition, and it obviously depends on the function. So this, I'm going to define it to be summation mi times delta ti. Delta ti, recall, was the width of the rectangle, right? And my I is ranging from 1 to n, and I'll also define my upper sum, which is going to be summation capital Mi delta ti. Okay, again, I varies from 1 to n. Capital Mi, recall, is the supremum f of x. Now, what happens if you refine your partition? By refine, what I mean is if you have if you started off with a partition t0, t1 all the way up to tn, right, which is b and this is a. What if you add in some points here? You add in another point, a point which wasn't there. That is, you take another q which contains p, right? If you take a q which contains p, then it would be a nice exercise for you to try out. You can in fact show that this upper Riemann sum is going to come down, right? This uqf is going to be less than or equal to upf, and this lower Riemann sum is going to go up. Sorry, this should be L. Okay, and this is something which is consistent with our notations, right? So as the number of partitions, as the number of intervals in your partitions increase, you want a better and better approximation. That is, you want the lower sums to go up and you want your upper sums to come down, correct? And that is precisely what is being conveyed here. And this, in fact, you get it. So far things are good, right? Now, what next? How do you, so now you have partitions. These partitions, they're just talking about you're dividing your interval into finitely many things, right? So now to be able to define the integral, I need to take the limit of it, right? So as your n goes to infinity, you get a better and better approximation, right? So that is precisely what we do now. So what we'll do is, so recall again that your upper Riemann sums are going to come down and lower Riemann sums are going to go up, right? So since the upper Riemann sums are going to come down, there should be a minimum value below which they cannot come down further, correct? That is, there exists some infimum, right? There exists an infimum for this upper Riemann sums, UPF, when you take the infimum over all such partitions, right? What I'll do is I'll call this the upper integral. I'll just denote it this way, whatever this means, okay? That is, the integral cannot be so this bounds the integral above, right? That is, the integral cannot be greater than or equal to this value. Similarly, the lower Riemann sums will increase, right? And the lower Riemann sums cannot increase beyond a particular value. So that is what we will do here in LPF. We take the supremum over P, right? Supremum, again, recall, is the maximum over all partitions, and we denote this as the lower Riemann sum. Okay. Now, when is the case nice? The case is nice if these two are equal, correct? The lower Riemann sum will keep going up and will hit a point, and the upper Riemann sum will keep coming down and hit another point, right? If the points at which these two meet are equal, then that's something where everything is very nice. And that is precisely what is called an integrable function. A function f is integrable if the two are equal. Okay. Oh yeah, sure, Shakti.
Is there something special about using this LPF and UPF, or they are just notations?
Oh, the LPF, UPF are just notations. U stands for upper sum, right? And L stands for lower sum. So if you recall here, these blue rectangles, if I add up their areas, I get L. And all the red rectangles, if I add up their areas, I get A.
Oh, yeah, got it.
Okay, thanks for the question. Okay, so a function f is said to be Riemann integrable if these two coincide. Okay, so let's not. So there's a lot of theory which you can do in Riemann integrals, but let's not get into that. That's almost a month's course in CMI. Okay, so what's the key idea again? What we did is we partitioned the domain into intervals, and we started summing over the areas of these rectangles and took the limit. Right now, this begs a question: what if instead of partitioning the domain, we partition the range. How bad are things going to get? Okay, this is one question which we will answer right now. Okay, that is, instead of partitioning the domain, what if we partition the range?
So like that means the y-axis.
Yes, the y-axis. What if we partition that? Okay, so for this, instead of taking a continuous function, what I'll do is I'll take what is called a simple function. A simple function, by definition, means a function whose range is finite, right? So for example, I'll just draw the graph of a function and then it'll make sense. So it's something like this. Okay, a function whose range is finite is said to be a simple function. So let's just take, for example, the value here is y1, the value here is y2, the value here is y3, and this is y4. Okay, now so recall again that this is a function, so it can't be something like this. Okay, that is a single point cannot take two different values.
Yes.
Okay, great. So now what we can define, so this is a simple function, recall it has only finitely many values, right? So let's say the values it takes are y1, y2, all the way up to yn. Okay, it's some finite number. Okay, what we'll define is the inverse image of this. So how do you find the area here? To find the area under the curve, what you'll do is you need to first find out what is this going to be, right? You need to find this area, add it with this, then add it with this, and finally add it with this, correct? So that is precisely what we do now. What we'll do is let's call AI to be, oh, someone used to complain that blue isn't visible. So, right. So let's call AI to be the inverse of YI. Okay. So in some sense, what is this? This is going to be my set A1, and this is going to be my set A2. This is my set A3, and this is my set A4. Okay. Now, what is my area? My area is simply, if you observe the diagram, summation yi times length of AI, correct? Right. So this is what my area is, but we will run into an issue. The thing here is nice, but the problem is these AIs need not be intervals. That is, if you take the inverse image of something, it need not be an interval. It can be something like the following. That is, you can have two different things here, and you can have a function. You can have something like this, right? So if this is y1 and this is y2, it is f inverse of y1, that is a1, is a disjoint union of two intervals, and f inverse of y2 is a disjoint union of two other intervals, right? Or for that matter, you could have such a weird looking function. You could have this function that is 1 when x is rational and 0 when x is irrational. This is a simple function, right? It takes values 0 and 1. The inverse image of 1 is the set of all rational numbers, and the inverse image of 0 is the set of all irrational numbers. So you could have all sorts of weird functions like these. And so if you do this again, what will be your notion of length? What will be your notion of area? It will be 1 into the length of rational numbers plus 0 into length of irrationals, right? And just for sanity's sake, let's just intersect with 0, 1. Okay, otherwise, okay. So this is going to be my area, correct? Now, so our goal today will be to formalize. So now you see why the notion of length is something which is really needed, right? So to define something as simple as area, we really need length. So what we will do is see does this make sense? Does the length of the set of all rational numbers make sense? Okay. This is something what we will attempt and do today. Okay. So now I think at this juncture, I should remark that if you take any positive function, that is, if you take any function, there exists a sequence phi n of simple functions, that is, functions with finite range, that increase to your function f. This is a rather non-trivial proof. That is, it can be done, but it's something which requires effort, right? That is, given any function, you can find a sequence of simple functions that increase to that given function, right? So in some sense, it suffices to study the theory of simple functions, and you can simply take limits, and you can get for any function f. So this goes a lot into measure theory, and this in some sense will be the crux of the course. That is, if you take
Aniruddhan, I just wanted to quickly ask, what do you mean when you say that the functions that your sequence slowly increases to your, like, what does it mean that it increases?
Yeah, I have the same question.
Oh, thanks for the question. It point-wise increases. That is, for any x in the domain, phi n, you say phi n of x. Phi n of x will keep going up. That is, phi 1x is less than or equal to phi 2x is less than or equal to phi 3x, and so on. And so you get a sequence here, right? So consider this sequence, phi 1x, phi 2x, and so on. And this guy is going to converge to f of x for each point in your domain of definition.
Right, and it has to like be an increasing sort of sequence.
Yes, it has to be an increasing sequence.
Sorry, phi is a set of simple functions.
Yes, phi is a simple function. This phi n is a simple function.
I see, thanks.
Okay, that is, recall a simple function is just something which has a finite range space. Okay, so let's not get into all this. So it's okay even if you don't understand this part. I just said it. So the idea is that it suffices to study just the theory of simple functions, and then you can just take limits. And this will be like your core part of measure theory. So if you take a proper 1 semester course on measure theory, you'll see 3 main theorems. It's called monotone convergence theorem, Fatou's lemma, and dominated convergence theorem. So that just writes out fully that you can in fact do this. That's one of the major goals of measure theory. But let's not delve into that side at all. Okay. So as of now, I hope all of us are motivated enough to study the lengths of subsets of R.
In that, x is a fixed number, no?
Yes, x is a fixed number here, and it works for each x in your domain.
I just kind of want to, and maybe this is an unreasonable request, but could you like make sort of, I don't know, like an intuitive sense out of this? Because I mean, okay, I kind of get it, but it seems a little contrived. Like, is there a intuitive?
I'll do one thing. I'll take this question towards the very end because it'll be a slight detour.
Okay.
I'll take this question towards the very end, and just send me, just remind me. Okay. So for now, yeah. So now we have enough reasons to study lengths of subsets of R, right? But now, like just saying that we want to study the lengths of subsets of R, many more questions arise. So the first and foremost question is the notion of length that we are going to define consistent with our intuition? That is, the length of open 0, 1 is 1 minus 0, which is 1, and the length of open AB is B minus A. Is our notion of length, we want it to be consistent with our intuition, correct? And secondly, this is the one question which is my personal favorite. Can we define lengths to all subsets of R? Okay. And the third question which we want to answer is, what properties do we want the formal definition of length to satisfy? Okay.
Yeah, so like in higher dimensions, you mean?
Oh no, I'm just going to stick to R. So
Okay.
nowhere I'm not switching out to any higher dimension. We'll just do everything on R. And maybe at the end, if there is interest, I can remark of how you can do it in higher dimensions. But in fact, like it's going to be, you'll realize that it's the same theory. That is, if you develop a theory on R, the same theory is going to very naturally carry forward to giving your notions of area, volume, and hypervolume, if I can call it, or whatever, right? So in fact, it's just complete in 1 dimensions. Okay. Good question, by the way. Okay. Now let's see. Coming back to the third question, that is, what properties did we want the formal definition of lengths to satisfy? Let's start with that. So what are some natural conditions? So let's just agree to call length as lambda for now. Okay, it's painful to write 6 letters every time I want to talk about length. So let's just agree to call it lambda. The basic property we want is that the length of an empty set has to be 0, correct? Otherwise, the theory is going nowhere if it's some finite number. Next, another property which we want is that this is something which you obviously want, right? So there's a reason why I took closed B and open A, but let's not get into all this theory again. Okay, so length of this interval A comma B has to be B minus A. This is something naturally which one would expect. And another thing which we would expect is, if you have a collection of intervals which are disjoint, you want their lengths to add up, right? What I mean by that is, if AN is a sequence of pairwise disjoint subsets, right? I'm not restricting to intervals here, because my goal is to define length to a class bigger than just intervals, right? So if I have a sequence of pairwise disjoint subsets of R, then what I want is the length of this disjoint union to be equal to the summation of this length. Okay. Now there is one more remark I'll make here. So this is again a slight detour. Okay, for those interested, you can contact me later. So why do we need a countable union, or why not just stop to finite union? So in fact, there is one whole branch of probability theory called finitely additive probability, wherein you demand just finite unions instead of countable unions. And this is something which Karandikar has extensively worked on. So he has done this whole lot of things on finitely additive probability, and he is the go-to person if you're interested in this.
No, first of all, why do we have to define length for subsets only? How does this make sense?
Other than subsets, what other objects can you think of?
No, like points. These lengths definitely make sense between points. Like how does it make sense with between subsets?
Okay, so I have two interpretations of what you said here. Length between points is just going to be an interval. Okay, and
Yeah,
the
yeah.
second interpretation is the length of a point. A point is a subset. So we will ultimately end up defining a notion of length of a point also. Okay, we'll get to that. Very good question again. Okay, so now recall, what were our three demands again? Our first demand was that the length of an empty set is 0. And then we wanted the length of this interval a comma b to be b minus a. And ultimately, we wanted length of a disjoint union of an to be the summation of the lengths of an. Okay. Now, are these demands, you agree they're reasonable, right? They're not too bad. These are some obvious properties which you would want. Maybe like one place where you would argue is why argue for infinite, and why not just settle with countable? So that will take us on a different route. But you agree that these are reasonable demands, right? Turns out it's not. These demands are not reasonable. So with these three demands, you cannot assign lengths to all subsets of R. Right? The problem is R has way too many subsets. Right? So what? Where does this? Okay, let's see where the issue comes up. The issue mainly comes up because these sets have to coexist with each other. I cannot simply take a subset of R and say this is your length, and I can't take one subset of R and say this is your length. The problem comes because of the third condition. In the third condition, I want the sets to interact nicely with each other. Correct? That is, if I take a countable disjoint union of these sets, I want it to interact with each other nicely, so that even after I take the countable disjoint union, the sum of that length is going to give me the length of the union, right? So in some sense, what it says is that you want the sets to behave nicely with each other, correct? Now, so where can we loosen our assumptions? That's the question here. Okay, that is, can we should we ask for something weak? Should we ask for something a little bit? Should we change our what we require of length, or where should we change our request? Right, that is a question. So the problem comes from something which is unexpected. It is that we asked for lengths of all subsets of R. That cannot happen. Okay, so what you can do is you can take a subset. Let's just, I don't know what to call it. Let's just call it L. Okay, you can take a subset L of 2 to the R. Recall 2 to the R is just the power set of R. Okay, the set of all subsets of R. You can take a strict subset of this and assign lengths to it. And if you assign lengths to just L, everything will be nice. The theory works out. Okay, and this is what we will see in this. This is like what we will do until the very end. The question to answer is, what is L, and what is that set which is in 2 power R which is not in L? Okay, so these are the only two questions which we will be answering until the very end of the
Oh, R
Oh,
is
okay. So we have to find what is L.
Yes, we will kind of see what is L.
Okay.
R is the real numbers here. Right?
Yes, R is the real numbers. R has been the real numbers ever since the start of the talk.
Wouldn't that 2 to the power R be very arbitrarily large?
Yeah, it's massive. L is itself something like which is ridiculously large.
So by 2 to the R, he means the power set of R.
Yes, 2 to the R is power sets of R. That is the set of all A subset R.
So you mean that you're supposed to find a subset for which the third condition holds?
No. So what I'll do is, maybe we will talk about it. So this is kind of giving a spoiler. I'm not going to do it now. Okay, this is reserved for the last 5 minutes of the talk. Okay, so
Okay.
yeah. Okay, so any questions at this point, just feel free to shout. So maybe a good point to catch me back up. Yeah.
No, just a quick clarification. So L is then just a collection of subsets of R.
Yes, L is a subset of the power sets. L is some collection of subsets. We'll see what L is later.
Yeah.
Okay.
Yes, but then this also means that it could be like a uncountable union of sets also, no?
Oh, you will see that it is an uncountable set.
Right.
It is uncountable.
I have a question. Like, are we trying to find the largest L, like which satisfies the first three properties?
That's a beautiful question. That's a beautiful question. So in fact, there will be a set which is bigger than L, but we will be happy with L. Okay. In fact, there is a set which is bigger than L in all sorts, and you can assign a notion of length to it. But the theory of that is just going to take us on a very, very big detour. Okay.
Wait, I don't understand. Can't L? Why are we saying that L is large? Can't it just be like just an arbitrary subset of R? Like it could be anything, right? Why are we assuming it's large?
No. So I think see, what I was trying to say is we first need to define lengths to some certain subsets of R, correct? What I was trying to say is that you cannot define lengths to all the subsets of R, right? That is, there exists some set in the power set of R for which you cannot give a reasonable notion of length. Because
so that's the there exists. Okay,
yes.
got it.
And the reason why you can't do that is because it doesn't interact well with the other sets. Right? That's okay.
So L is the complement of the subset, that is the useful subset.
Yes, L is basically like all the useful subsets, the sets to which you can define length nicely.
What do you mean by interact with the other sets?
Okay, so see, what I was saying is that so let's just go back to what I said earlier. So you cannot simply pick a set out of 2 to the R and say this is your length, right? You can't simply say pick the open interval 1, 2 and say go home 5 is your length, right? You cannot pick, say, the set of all rational numbers and say your length is 23, right? The reason you can't do that is because we demanded that something called countable additivity holds. We insisted that if you have a collection of disjoint subsets, the length of their union is going to be the sum of their lengths, right? So for example, if you take the set 1, 2 and if you take the set 3, 4, suppose you assign the length 1, 2 to I'll just take this. So you take 1, 2 and you say 3, 4. Okay, you assign the length of 5 to 1, 2, and to 3, 4 you say you assign the set 11. Okay, you set 7. Okay, now the another subset of R which you picked out is, let's say, 1, 2 union 3, 4, and for this you assign 23. Okay, this is sheer madness, right? You don't want this to happen, right? So what we will do is we'll not.
No, how is this sheer madness there? Because we are defining 5 and 7, and then why we cannot define 23?
No, but I mean, like it's not nice, is it? Like you have, okay, I think someone pointed out. Yeah, Anand, very good point. I have a pen, I have an apple, now I have 2 apples. So in some sense, like you have one set, you have one apple, you have another apple, you suddenly can't expect 4 apples, right? 1 plus 1 is going to be 2, at least reasonably.
Yeah, but that is physical. But here we are quite abstracting.
Oh, let's just stick to some intuition we have. The goal again is to build on the intuition we have.
Yeah, okay.
Right? Okay, that's a good question, by the way. Okay. Okay. Now, what I was saying is that this L, basically this 2 power R has way too many subsets to even imagine, right? So it's going to have so many subsets which I'm never going to encounter in my life, right? So what are some of the subsets which I'm going to encounter in my life? I'll obviously see intervals, right? So I would want a notion of length for my intervals. Otherwise, just throw this theory to the trash if the intervals do not have length. Okay. And what other sets are interesting? So if I have a sequence of sets which are interesting, then I need their union also to be interesting, right? So in some sense, so this measure theory has very much of its applications in probability theory, right? So if you think of your measure lambda as a probability of some event happening, and if you think of some set A as an event, okay? So lambda of A basically gives you the probability that that event happens, right? So in some sense, if you have a collection of events, a natural thing to be interested in is what is the probability that at least one of these events happen, correct? So if you have a sequence of sets AI, then a natural thing to expect would be to assign a length to what is the union of all these sets, right? And similarly, if I have an event A in probability, or if I have a set A in measure theory, you would also expect its complement, right? What does the complement do? Or the complement takes us, what is the probability that this event does not happen, correct? So these are some three reasonable things which I would expect, right? I want to be able to assign lengths to these elementary sets, which are intervals. And if I assign lengths to all these AIs, and I want to be able to assign a length to this union of it also, right? And if I assign a length to A, then I want to be able to assign a length to A complement as well, right? So now this A comma B is for all A and B in R. I'll take all open intervals, okay? Turns out, now what do we need? We need to assign lengths to all these subsets of R, right? So turns out there is a subset. Okay, so 2 power R contains all this, right? 2 power R is closed under countable union. 2 power R is also closed under complement, right? A question we're asking is, does there exist a smaller bag, right? Does there exist a smaller set in 2 to the R, which contains all intervals, which is closed under countable union, and which also is closed under complement?
Hey, I just have a quick question. Sorry, about the third axiom, right? Taking the complement, are you doing it with respect to R or some kind of finite set?
R.
Okay.
Yeah, thanks for the I should have said that early on. A complement is just R minus A. Okay. How am I doing on time? 40 minutes. How much more do I have? Okay, I think I'll be able to finish, but okay. So
hi. Are we allowing infinity to be a length?
Okay, we will allow infinity to be a length, but I think let's not.
Yeah, that's exactly what I was asking.
This is a very good question.
Yes, we will allow infinity to be lengths. That is, like if you take intervals like this, 1, 2 union 2, 3, and say n, n plus 1, and you take a union of all this. Right? This is going to be a cover, right? So it's going to be infinite. Okay, so infinite.
Is it intuitively right?
Yes, it is intuitively correct. So, for example, if you have a function, okay, which is 1 throughout, what will be the area under the curve?
Oh, okay, yeah, this is 1 times infinity.
1 times infinity. So that's one of the reasons why I put 0 into infinity. I put that later, if you noticed. Okay. So right. So what are we demanding? We demand to find a nice bag of subsets. Let's call it B. Okay. It should contain all open intervals. And if you have a sequence, it should have its union. And finally, if you have A, then it should have its complement, right? So one obvious subset of R is also one obvious set is 2 to the R, which is a set of all power sets, so the set of all subsets, right? So this is one obvious subset, but can we go for something smaller? Does there exist something smaller? In fact, it does. Yes.
Yeah, I mean, okay, I should not have said this. Is just I'm derailing. Maybe just I kind of wanted to put in a candidate here, which is maybe so. Is an answer to be the set of all intervals and all the interval complements, open interval and complements of open interval.
Okay. What about it?
So is this a candidate for B?
Yes, in fact, yes. Okay, so we'll do this. Okay, so give me one. Allow me to say one line, and after that, you'll answer your question yourself. Okay. So now let's see one interesting property of. Okay, so what B is basically the smallest bag, right? Why does the smallest bag exist? The smallest bag. How can you construct it? You simply take the intersection over all these sets which contain B. Okay. And that is what you get, right? So what am I saying? Oh, no, wait, what am I saying? So so let's say there is so the way you construct the smallest set is simply you take the intersection of all the sets which satisfy these three hypotheses, right? And observe that this behaves well under intersection, right? So if this doesn't make sense, I'd say just accept it that there is a smallest bag B, which is a subset which is smaller than 2 to the R. Okay, just take it for granted that there exists such a small bag B. Okay, this small bag I'm saying, but it in fact has so much. Okay. So now this bag B is called the Borel sigma algebra. I have tried to reduce the number of fancy terms I've used, so only the most important terms I'm using. So a sigma algebra is simply a collection of sets which satisfy the 3 axioms, right? And Borel simply says that the first axiom demands that you have open sets. Okay, so Now, so this is what is called the Borel sigma algebra. So now coming to Rajdeep's question. So in fact, a nice, maybe like a small observation which we can do now is that if you have a collection AI of sets in your Borel sigma algebra, okay, recall again, each element in the Borel sigma algebra is a subset. Okay, so this is a subset of 2 to the r. So just spend your time thinking about this. Okay, then it's closed under intersection also. So we demanded that it's closed under union. But what I'm saying now that its intersection AI is also in the Borel sigma algebra. And any quick proof?
De Morgan's law.
Exactly.
Fantastic.
Complement.
Fantastic. Right. So AI, I know that each AI is in the Borel sigma algebra. That means since the Borel sigma algebra is closed under complementation, AI complement is also in the Borel sigma algebra. Now, each AI complement is in the Borel sigma algebra. So union AI complement is in the Borel sigma algebra. And now again, it's closed under complementation. Union AI complement, whole complement is in the Borel sigma algebra. But this is precisely intersection AI. Okay, fantastic. Okay, now Rajdeep, has your question been answered? You started with all open sets and you're taking the closed sets as well, and you're taking your union or something of it. Correct?
Yeah.
Okay, great. So now let's talk about this Borel sigma algebra. This is the mystery object to us. So what do we want? Remember, our goal is to simply assign length to the Borel sigma algebra. Correct? This is what we want to do. And you'll see that this guy itself is massive. It contains all the imaginable sets you can think of, right? So let's see what all sets are in this bag. So can someone give me an argument as to why any singleton is in this bag?
Intersection of open intervals.
Intersection of open intervals. What would be the open interval you're taking?
Wait, are we only alone? Because okay, so didn't we start with half open intervals?
No, you can mix them. Okay, in fact, okay, so you can in fact, okay, let's say if it is a comma b you started with, so what would be your singleton? What is it the intersection of?
Nested intervals.
Yes, nested intervals, right? You take a minus 1 by n and a plus 1 by n. Okay, so if you haven't seen this before, a nice exercise would be to try and prove it, right? I think Archimedean property or something you can use, and you can just see this, right? There exists a natural number bigger than every number, right? So with that, this will be done, right? Now, so all singletons. So think about just keep this Borel sigma algebra in mind, okay? Every single singleton is there in the Borel sigma algebra. So that itself tells you that the Borel sigma algebra is uncountable. Correct? It's massive. Next, the set of all. Okay, now
when you are writing that singleton, n is an integer or like any real there?
Oh, here n is an integer. N always is a natural number rather. That will be easier. Okay, a is any real number. Okay, every possible singleton for all a belongs to R. So that itself tells you that this Borel sigma algebra is uncountable. Correct? Now, every possible countable set. Can someone quickly argue why every countable set is in the Borel sigma algebra?
Union, countable unions.
Fantastic. Every countable set is a countable union of singleton sets. Okay, I can't believe I had to. Okay, first time I'm saying this. Every countable set is a countable union of singleton sets. So that's there. Next. Coming back to, I think, I don't remember who asked the question. So in fact, you can say that if you just start with your initial demand was with just a comma b, right? So you can in fact prove that this a comma b and this a comma b and a comma b are all elements of the Borel sigma algebra, because you know that a comma b is there and singleton b is there. So this is going to be guaranteed, and this because singleton a is there, and this because singleton b is there. Okay. So all sorts of all intervals that you can think of are there in the Borel sigma algebra. Correct? Next, this is something which is slightly tricky. So all open sets are there in the Borel sigma algebra. Why is it? This is slightly tricky. I'll wait for a minute.
I know this fact. I don't think I remember the proof that maybe all the open sets of R are actually just countable unions of open intervals.
Why is that?
Yeah,
because that's how you define the real numbers, I guess, with this underlying.
Can we back up what's an open set?
One at a time. Your voice is really. Anand, I didn't hear you until now.
No, is it like when you construct the real numbers, you have to have this kind of property where all the open sets are some kind of union of.
Wait. Are you sort of importing the definition of an open set from topology, that every point has a has a neighborhood contained in the set.
Yes, but I'm looking for just one answer, just one statement which says that every open set is a countable union of open intervals. That is, what should be there in every open interval?
Can you recap? What's an open set? I mean,
Oh, what is an open set? Okay, then let's not get into this topology part. So this is why I put this tag here. So if you're fantastic, who said that?
Rohan.
Awesome. So the idea is that if you write an open set as a disjoint union of open intervals, each open interval you write must have a rational number, correct? So in some sense, it's the number of open sets you have is bounded above by the number of rational numbers, because you should have at least one rational number in each. So just think about it if this doesn't make sense. So it's okay, like even if you don't get this and the next argument, okay? So each open set is a countable union of open intervals. Oh, my handwriting, okay. Now a closed set can, this is a rather, once you understand why open sets are there, why are closed sets there?
Complements of the open set.
Fantastic. Right? This requires topology. So these 2 points require topology. So it's okay even if you don't follow this. Okay. So closed sets are simply the complements of open sets, and so closed sets are also there. Okay. Now let's come to something interesting. Okay. So just take a stock of the situation. What all did we have in our Borel sigma algebra? We had all the singleton sets. We had all the countable sets. We had all the intervals of any kind. Then we had all the open sets, we have all the closed sets, right? And it's closed under what all? It's closed under countable union, it's closed under countable intersection, it's closed under complements, and it has all the intervals, right? So this is what a Borel sigma algebra is. Now, one interesting set we will see is, in fact, I think I'll just skip this and say that, show that the Canterset is in the Borel sigma algebra. Okay, this is a rather easy argument from what we have done so far. So this is something which you can do. Okay. So for those who aren't, yeah, okay. So Canterset, I'll just quickly describe. So you start with the closed interval 0, 1. Okay. You delete the middle 1/3 interval, that is 1/3 and 2/3. You delete so that you're left with this interval. Okay. Now from this you delete the middle 1/3. Okay. So, oh God, help me. This is 1/9, this is 2/9, and this is 7/9, and this is 8/9. Okay. So at the end of 2 steps, what you'll be left with is something like this. Okay. This distance is 1/3, this distance is 1/9, and this distance is 1/9, if I get my math right. Okay. So you continue this process indefinitely. Okay. And ultimately you take up the intersection of all these. That is this, let's call this C0.
I mean, isn't this just a...
Isn't this just?
Yeah, isn't this just a countable union of closed intervals?
Yeah, that's it. That is literally all there is. But the reason I introduced Canterset is to give you a little bit more to think about. Okay, so you take the intersection of all these CNs, and what you'll be left with is this set called the Canterset. Okay, so now, so in fact, like a couple of nice exercises which you can do. First, show that oh God. First, show that this C is in the Borel sigma algebra. Okay. And secondly, this is the first exercise. And the second thing what you can possibly try is that every point of C is a limit point. So don't spoil it for those who want to try. So every point of C is a limit point. Okay. Limit point, again, recall, is that there exists some sequence of points which gets close and close to that point. Okay. Next, this is something fun. C is uncountable. Okay. So the hint to this will come in the next problem. So use the next problem to do the previous problem. Okay. So for this, what you'll do is, just give me 1 minute. I hope I don't mess up the notation. Okay. So for this, show that if you take an interval, if you take a point in this closed interval 0, 1, right, you agree that you can write a ternary expansion of it, right? That is base 3 notation, similar to how you expand in base 10 notation. You try and expand in base 3 notation. So that means you can find a sequence xn such that this xn over 3 to the n converges to x. Okay. So if it's okay even if you don't have this formal definition of it. So just think of it intuitively. This xn over 3 power n goes to x. Okay. Now this Canterset show that it is precisely, our definition and this definition is the same, show that it's precisely the set of all closed interval x in 0, 1 such that there is an expansion of x with no ones. Okay, the Canterset is precisely the set of all those numbers in 0, 1 such that there exists an expansion of x with no ones. And why is it intuitively obvious? It is intuitively obvious because if you have a point here, you can simply trickle down this, right, and reach that point. And every point, we said this in some sense gives you a hint as to why every point is a limit point also, right? So I'll not spoil it any further. So once you show this, so this is one thing which you can do, and ultimately a final exercise about the Canterset will be to show that it does not contain any intervals. Oh, where do you people disappear? Oh, okay, good. So that this Canterset does not contain any intervals. It may be easy for those who have seen it already, but it's okay. Let's just move with it. Okay. So now, what is the length of the Canterset? Any quick answers?
You would want it to be 0.
Hopefully, it should be 0.
You would want it to be 0.
Yes.
Exactly.
And why is it 0?
Okay, you take the full Canterset. It's, if you take 1/3 of it, it's the same set.
Right.
Kind of.
That's a good answer. That's a very good answer. So in some sense, this Canterset you can say zoom into just this part. Okay. So treat your old 0 to 1/3 as your new 0 to 1. Okay. So then its children are going to look like the original Canterset itself, right? So this is one reason why you would want it to be 0. And another maybe like a slightly more maybe like a writing down answer would be something like C. What is the length of C0? Length of C0 is 1, right? You just started with this entire interval, right? So this is how you went. Okay. Then the length of C1, the other C, is just 2/3, right? And this length of C2 is 1/9, 1/9, 1/9, 1/9, 1/9, 4/9, right? So you'll agree that the length of Cn is 2/3 to the n. Why is it? Because each Cn is a disjoint union of 2 power n subsets. No, yeah, 2 power n subsets of length 1/3 power n each. Okay, this is something I think that you can do using induction, or this is something like which you can rather very easily see, right? And so this is the crucial part. And how are these sets arranged? C1 contains C2, contains C3, contains C4, and so on, right? And what I see, C was simply the intersection of all these. So so you agree that this length of Cn goes to 0, correct? Because it's simply 2/3 whole to the n. And it's becoming smaller and smaller and smaller. So you would want, as Rohan pointed out, the length of the Canterset to be 0. Okay. Oh, I think I should have said this early on. Firstly, convince yourself that the Canterset is non-empty. Okay. Canterset is not empty. It's uncountable. Okay.
You proved it. You asked us to prove it's uncountable, but did not mention that it's non-empty.
Yeah. Okay. So right, so maybe let's just convince yourself, if you're not already, just it's non-empty. Okay, so things what we're talking about is we're not drunk. Okay, okay, so far so good. Now what have we got? We have got an uncountable set that contains no intervals and has length 0, right? In other words, Canterset is just dust. Okay. Okay, so now let's see another example of a set with 0 length. So this is going to translate back to someone who had asked for the length of a point, right? So let's just see a slightly more generalized one. So you take the set of all rational numbers, okay? And now what you do, you know that the rational numbers are countable. So you can enumerate it as R1, R2, R3, and so on, correct? Now let's fix some epsilon greater than 0, okay? Then what you're doing is you have some R1, R2, R3, R4, R5. I'm just not drawing it in order so that you don't get the wrong picture. Okay. So what you do is around R1, you construct a ball. Let's just say around Rn, you take this ball, Rn minus epsilon by 2 power n plus 1 and Rn plus epsilon by 2 power n plus 1. you take this interval. Okay, so in some sense what you're doing is you take R1, you consider a ball of radius epsilon by 2 square around it. Okay, you take R2 and you take a ball of epsilon by 2 cube radius over it, around it. You take here and you take epsilon by 2 power 4, here epsilon by 2 power 5. And I think it is rather it's not very difficult to see that your Q is contained in this union, correct? Because simply because Rn is in this interval, right? Now this is where the fun part is. The length of rational numbers, if you could assign something to it, is going to be so see, length is something which we want it to satisfy nice properties, right? One nice property we want is if A is contained in B, then length of A should be utmost length of B, right? We don't want a superset to have smaller length than the subset. That will be ridiculous, right? So since Q is contained in this, we want this to be less than or equal to the union of this. I don't know why I put the by here. I'll just put 1 here. Okay. So now this convince yourself is going to be less than the sum of these individual lengths. And if you can't read, this is epsilon and this is an n plus 1. Okay, I'll write my hand. I'll improve my handwriting. Okay, why is this less than or equal to this? Because the balls which you take around each Rn, in some sense they touch each other. So the part where they touch each other, you're counting them twice, right? So this is a strict inequality. And what is this equal to? This is summation over n. The length of this is going to be epsilon over 2 power n, correct? And n we took, I think, from 1 to infinity. This is going to be epsilon or 2 epsilon, it doesn't matter, right? So what have we done? We just said the length of Q is less than epsilon for all epsilon greater than 0. Okay, and so this would necessarily mean that the length of this, negative numbers don't make sense. Please don't start that now. Okay, negative lengths do not make sense. So I mean, it makes sense. So in fact, even complex lengths make sense. So once you take a course in measure theory, you'll even see that you can assign length of a set to be a complex number, but please don't get into that from now. Okay, let's have some sanity, and this is an expository talk. Remember that. Okay. So this proves that the length of all rational numbers is 0. Okay. Now, in fact, this argument can be extended to something even further. You can simply say that the length of any countable set is 0. You can simply write the exact same argument without any change, right? You can simply replace Q by S, and where S is any countable set, right? So what have we seen? We've seen that length of any countable set equals 0. Okay. And now you agree that, now what did we start off with? This Borel sigma algebra, remember, contained the set of all countable sets, right? Now answering your question about the length of a point, right? The length of a point has to be in some countable set. A countable set has length 0, so the point has length 0, right? That is, I think, this way of touching your nose. And I think easier way of touching your nose would simply be to say this singleton set A is going to be contained in A minus epsilon by 2 power n plus 1 and A plus epsilon over 2 power n plus 1. And you can simply...
Why do you need the powers now?
Okay, good point. Yeah.
Okay, sorry if this is a dumb question, but
no, it's okay.
Yeah. So since Q is a countable set to begin with,
Yeah.
couldn't we just treat it as a countable union of singletons? And since we started off by defining singletons to have 0 length, so you are adding countably many zeros.
Okay, we didn't start with singletons having 0 length, did we? Oh, right. We could have simply I defined A comma B as B minus A. That's a good point. We could have done that. Yes, that's a very good point.
So we just summed, because we also took the sanity condition. So
absolutely. That's a very good point. This is far from a stupid question. This is me being stupid instead of Okay. So what have we shown? We have shown that any countable set has length 0. Okay.
Actually, no, unless you use that construction, right? Like you can't show that it's finite, right? Like let's suppose everything is like epsilon by something, it may not converge, right? Like the interval that you construct around each singleton set, right, in the rationals, unless you order it and, index it in a certain way and use the construction you did, right? You may not be able to rigorously prove that.
No. So what he's saying is the following. You see, one thing which we agreed upon is we have this closed interval a comma b in our Borel sigma algebra, right? And we assign the length of any a comma b. This is our sanity condition, which is b minus a, right? Now, so this singleton is simply a comma a.
Okay,
Correct?
okay, that way.
So
right.
the length of each singleton is a rational is 0.
Okay, okay.
Right?
Okay,
so
I
if you
didn't
take a countable
catch that,
union of
right.
0 is 0.
Fair. Okay. Shit, I didn't catch that. Sorry, I thought you meant construct an interval around
No.
each of the
You don't need to
singletons.
construct an interval around this if
Okay,
you take
cool,
this
cool.
approach.
Yeah.
Okay. So in fact, just keep this argument in mind. If we have time, we'll come to it at the very end. Like I plan to talk about it, but like if we have time, we will talk about it. Okay. So this will be used in the construction of a set which is not measurable. So the exact argument which you gave here. Okay, let's see. Now, what is our goal now? So we need to properly define length, right? So far we have been just talking about examples. Yes, Q is countable for now. S basically I just replaced S for any countable set. So the argument I gave was for Q, and I just said you can just replace by any countable set S. Okay, so Q is countable. Okay, so far we've been seeing a lot of examples about what sets are there in the Borel sigma algebra and all that, right? Now, how do we define notion of length? That is what we want to do now. Okay, now as it was just pointed out, for any interval a comma b, we want the length to be b minus a. Correct? Now, if you have a disjoint finite union of intervals, that is, if you have I1 disjoint union I2 and so on disjoint union Ik. Okay, so if this is your set, I is a bad notation, let's call it S. Okay, then it is sane to expect that the length of S is just summation length of I, or let's call it J. Correct? This is a reasonable assumption, right? Next. So we're just trying to define notion of lengths to bigger and bigger class of subsets. So we started with just the interval. We could define this. And now we're doing it for disjoint unions of intervals. We can define it this way. Right? Recall the right hand side is just a disjoint union of intervals. So this it's already defined by this. Right? Now there is a bigger problem. We want to define lengths to a bigger class of subsets. Right? So what we can do is, there's something like which is a common approach in analysis. So what you'll do is you'll simply define it for everything irrespective of whether it makes sense or not. And then you'll filter out only those things for which it makes sense. Okay, a very common approach in analysis. So what we'll do is for any, any spelling, why, right? Okay, any A subset R, what we'll do is we'll define its length. I'm not going to call it length as yet. I'll just call it some lambda star. Okay, lambda star is just telling that this is not yet length, but has the potential to become length. Okay, so lambda star, what I'll simply do is I have a weird looking subset here. Okay, so some places are here, some points are singletons. I have some ugly looking set. Okay, so what I'll simply do is I'll cover it by sets which are nice. Okay, so what I'll do is I'll cover this set A by intervals. Okay, and what I'll do later is I'll take the sum of these lengths of Ik. Okay, but I don't want this. This is going to be massive. I can make it as large as I want, right? I don't want it to go large. So what I'll do is I'll take the smallest possible number. That is, I'll take the infimum of this collection. Okay, so what I'm doing again is I'm covering this set A by a countable union. Okay, and I'm summing over the lengths of these intervals, and I'm taking the minimum over this. Okay, if I do this, this is what I'm going to assign as lambda star of A, whatever that means. Okay, so this is something like I think take a little bit of a time to get used to it. So what I'm doing is I'm covering A by countably many intervals, and I'm taking the least of the sum of the length of the intervals. Okay, so let this definition sink in. So note that we are not demanding that these IKs are disjoint. We do not need that. Why is it that we are not demanding? Why does just Ik do the job?
I think anyways when you take the infimum.
Fantastic.
Yeah.
Yes, anyways taking the infimum, right? Infimum in other words is just quote unquote minimum. Okay. So when you take the minimum over it, like if something has a decent enough overlap, so you can in fact find something like this. Right. So this infimum is going to weed out all the sets where this ik's are overlapping with each other, right? So recall again that I'll just write this definition again. So just tell me if this is not making sense. So what you're doing is, just one second, I'll just finish this and I'll take your question. I shouldn't mess up writing this. I'm taking the sum of lengths of all these intervals such that this A is contained in the disjoint union. So I'm covering A by these countably many intervals ik, and I know how to define this. This is well defined, and I'm simply taking over the sum and ultimately taking the minimum. Yes, question? None?
I just quickly want to confirm. So we don't demand that this sum needs to like converge to any real number, right?
Nothing. We're just defining this. This as yet doesn't make any sense. Okay. So we'll see. So that's what I said. So what you'll do is you're simply taking, you'll simply define it like without thinking. You're just going to define it for everything, and then you're going to filter out only those sets for which this definition makes sense. Okay. That is precisely what you're going to do now. Right. Okay. So now, in fact, like this is something which we have to prove that this is in fact that sanity check. We have to do it for this also again. That is, we in fact have to show that lambda star of a minus b is b minus a. This is a tricky argument. This is not easy, right? So what is one direction? So okay, another thing about an analyst is that an analyst always sees an equality as two inequalities. Okay, so you prove one direction, and it's almost always the case that one direction is trivial and the other direction is ridiculously hard. But this time it's not ridiculously hard, but it's hard. So hard that we'll not do it in this today's session. Okay, so which direction is trivial?
Enclosing in the interval and finding a larger interval, which is just a to b.
Exactly. So I think this, hopefully this is the trivial part, right? You can simply take one of the intervals ik to be a comma b, and say I1 to be a comma b, and ij for all other j to be the empty set, right? So a is going to be contained in the union. So lambda star is going to be the infimum of all this. So it's going to be less than or equal to that. Okay, so this is one possible cover. Now, in fact, you still can show that lambda star of a comma b is greater than or equal to b minus a, but this requires effort, right? This is not very immediate, but it can be done nevertheless. Okay, so let's see if I can manage to put it in one of your exams or quizzes.
Wait.
Yeah.
Why do we need ij is 5? Can't we just take like only one set, like I1 to be a to b?
Yes, that's what I took. I1 is just a to b, and ij is just anything. Ij, I just put it empty so that ij can be anything potentially. Yeah.
Oh, okay.
Yeah. So ij, I just put it to be 5 so that I get the best out of worst basically. So instead of adding all 9 plus 2 plus 3, I'll just add zeros everywhere for wherever I don't need to add anything. That's why I put the others as 5. Okay. So now, so yeah, question?
No, unmuted by mistake.
Okay, cool, no problem. Right. So what did we do here? I'll just write down this. Okay, should I write this definition again? I hope all of you are fine with it. So you simply take, I shouldn't make a mistake here again, length of ik, where a is contained in this union ik. Okay, let's just. Okay, now what did we do? This, remember, this is defined for all a subset R, right? This is the stupidity here. So for all a subset R. Now what we have to do is we have to filter out these intervals where things behave nicely with each other, right? We want sets to, remember the old argument again, we want sets to interact nicely with each other. So we want to filter out only those sets which behave nicely, right? So this is where enters the genius of this man called Carathéodory. So if you do measure theory, you'll see his name infinitely often, right? So this is where enters this guy, where he gave a rather trivial looking condition to say that you take all these sets which satisfy this condition and whatever you have will be same. Okay, so what Carathéodory gave is a condition. So if for each set he gave a test, okay, that test will, if the set passes the test, too many syllables, if the set passes the test, then it's going to be a good set, otherwise it's going to be a bad set. Okay, what is the test? This test looks obvious, okay, but the motivation for this, all that is going to take us on a too long of a road, right? So I'll just state what the condition is. So what it says is that you call a set A is measurable if for all E subset R, you have lambda star E equals lambda star E intersection A plus lambda star E intersection A complement. Okay, this is obvious looking, right? I mean, like E intersection A union E intersection A complement is E, right? So one would expect that if length of E intersection A and length of E intersection A complement, if you add up, you'll get the length of E, right? This is the problem if you try to do defining the length, this lambda star for every possible subset. You go to run into all sorts of hurdles, right? So if you're not able to visualize this, just see this as a Venn diagram, right? So what this is saying is, no, let's this is going to become too bad. Venn diagram is going to look ugly. So what this is saying is that if it satisfies this condition, then it behaves nicely. Else, throw it to the trash. Okay, this condition is stupid looking, right? So all what this is saying that if you have a set lambda star of E, lambda star, just remember the definition again and again. I'm going to use it throughout. Just write it down if you want. Okay, lambda star E is lambda star E intersection A plus lambda star E intersection A complement. And remember the distinctions between A and E. You want it to hold for all E, and you call this set A to be measurable. Okay, don't switch the roles of A and D. That will become an issue. Okay, thus if it satisfies this, you call the set to be measurable. Okay, now what is a natural object to consider? You simply take L to be the set of all measurable subsets. Okay, you simply take L to be the set of all measurable subsets. Now, where am I going? There is L, then there is this Borel sigma algebra B, then there is 2 to the R, right? Now, where am I getting to? Like, this seems to be going nowhere, right? So what is L? Let's study a little bit about L. So L, in fact, you can prove it will require effort, obviously. Like, you need to formalize everything what I said. In fact, this is also a sigma algebra. What is a sigma algebra? Recall again that it contains both empty set and R, right? Phi is an element of L and R is also an element of L. And if A is an element of L, then A complement is also an element of L, right? If AI is an element of L, then union AI is also an element of L, right? Sets of subsets which satisfy all three is called a sigma algebra. L is in fact also a sigma algebra, right? So this is something which you can prove. Now, here is the magic. What did we want to do? Our goal was to define lengths to all these subsets B, correct? That is what we initially started with. B again, what did it contain? It contained all open sets. It was closed under complement and it was closed under finite union, right? This was our B. Now, here is the fun part. The best part about all this drama we did is that this is a subset. Okay, remember I said we'll do it for all the useless stuff. This lambda star we defined for all the useless stuff, right? Then we filtered out using Canterset's condition to just L, right? Now we're further filtering out, saying I'll do all this nonsense, I'll get some smaller class of nonsense, and I'll get an even further class of nonsense which I'm interested in, right? So in fact, okay, this inequality is obvious. I think this inclusion is obvious. So now, okay, so I hope so far this is clear, right? So far so good. Any questions at the moment?
Just to
So
confirm,
in the
sorry.
measurable definition, was E also measurable, or like was it a random set?
No, E is a random subset of R. E is any arbitrary subset of R.
Okay.
Yeah. Rohan?
You're saying you can finish because you said like you'll need about 10 more minutes.
Oh, yes.
You can take questions in one go.
Yeah, I think I have only like about 5 minutes of your time. I'll finish. Okay.
No, you can take questions in one go is what I was saying.
Okay, cool. Okay. So I think this is just the last topic. So now what I'm going to do is construct a non-measurable set. That's the only thing I have planned. I'm happy that I was able to actually finish it. Okay. So what was the major inclusion we got? What we got was that the Borel sigma algebra is a subset of the Lebesgue sigma algebra, is a subset of the power set. Right? This is what we got so far. Oh, got as in like this is something which okay. So this inclusion okay. So this inclusion is something which you can. It's not very difficult to prove, and this inclusion is obviously obvious, right? Now, let's see. Now, what is a natural question to ask? Is it strict? Right? That's a very natural question to ask. Now, turns out both of these are strict. Okay, let's see the implications of both of them. What does this say? This okay, I'll start with this. Undo. Okay, so what does this say? This says that you started out wanting to define lengths to just sets in B, and you got lengths to a set to sets which are much larger. Right? So this says that you wanted something and you got so much more than what you wanted. Right? That's what this inclusion says. And this is something which will take into a little bit of, it will involve a lot of countability arguments. So I'll maybe if there is interest towards the end, I'll talk about it. But let's I think not worry about this now. Right? Our key interest, what I promised in the abstract also, is the following. That is this. There exists a set for which there does not exist any sensible notion of length. Sensible in the sense of whatever we did. Right? So our interest now will be to show this. Okay, given that we have showed this. So okay, this is obvious. So we'll show that this is not there. Okay, so for this, we need one small concept called translation invariance. Okay, so the first time I was introduced to this was by Manjunath Krishnapur. Okay, he's a prof at Indian Institute of Science, Bangalore. And the reason I remember this so vividly is that he gave this example. You're buying an idli at a self-serve canteen. You don't want it to shrink when you come back to the table. Right? That's what translation invariance is. So what it says is that if you have a set A, which is measurable, then A plus X, which I'm going to define by this set A plus X, where A is in A. Okay? If you define this, then the length of A, this also is in L, and the length of A is equal to the length of A plus X. Okay, and a remark here. Earlier I just used the notation lambda star for all subsets, right? Lambda star of A was for all subsets A in 2 to the R. Now for subsets, if this A in L, I'll simply call it lambda. Okay, so I'll just drop the star if the set is in L. Okay. Oh God, give me a minute. My battery is running out. My notes are here. Sorry about this. Okay, great. Sorry. So what translation invariance says is that if you have a set A and if you have the set A plus X, then the lengths of these two are equal. And this is something which is natural, right? Length of open 1, 2 is the length of open 2, 3 is the length of open 3, 4, and so on, right? So now this I think should give you a hint of where we are heading at it. Though it's far from obvious, right? So this is something which what we'll do now is construct a non-measurable set. Okay. You start with this G. Okay. The reason why I use the notation G, you'll see later. Okay. You start with this G, and on this.
Hi. So for this, can't we do it like the length for any set is defined by infimum of like the countable sum of intervals which cover it? So like if we have A plus X, then just shifting the interval, the lengths remain the same. So exactly. The infimum will also be the same.
Fantastic. That's it. Yeah, he's just given the proof of why why this lambda is translation invariant. Okay. So now what we will see is a consequence of this translation invariance to show that there exists a set for which you cannot define any same notion of length. Okay. So let G be this set, closed 0, open 1. Okay. I think it will work even with open 1, but let's see how. No, it won't work with open 1. Okay. So let's see what we'll do. So what we'll do is we will define. We'll put this closed 0, 1 into bins. Okay. That is, we'll take this entire closed 0, 1 here, and what we will do is we'll put it into different bins. Okay. So the bins are going to be like this, where X and Y are in the same bin if and only if X minus Y is a rational number. Okay. So in other words, what you'll do is you take an equivalence relation. Okay, you take x equivalent to y if and only if x minus y is a rational number. Okay, so if you don't know what an so an equivalence relation is basically like it satisfies all this. That is, x is you can see that x is similar to x is similar to y, implies y is similar to x, and finally x y z implies x z. Okay, if you have not seen all this, then it would be not very difficult exercises to prove them. Okay, and another exercise to prove would be that if you have an equivalence relation, it gives rise to a partition. Right, a partition simply is that you can write this close 0 open 1 as a union of some things. Let's say union of what give me some letters. I don't know, p alpha. Okay, for the lack of imagination. Let's alpha is in some indexing set. Okay, I don't want to get into all these details, but what this says, if you have an equivalence relation, you can write it as this union where p alpha is not p alpha intersection p beta is empty if alpha is not equal to beta. That is, these classes, these bins, these are called bins, let's call them, and these bins are disjoint, and the union of these p alpha is going to give me 0. Okay, so this is something which you can do using an equivalence relation. So something like with I think you can check, right? So for those who are familiar with group theory, so if you're not familiar with group theory, just ignore the next 2 minutes. Okay, so you start with open 0 or close 0 open 1 with addition mod 1. Okay, and you take H to be the set Q intersection 0 1. Okay, now you quotient this. Okay, so what do you get? You get a bunch of cosets, right? You start with this and you get a bunch of these cosets. Correct? Now, okay, now whoever doesn't know group theory can join back. So basically what you get is a bunch of bins, right? You get a collection of these. Okay, can someone quickly tell me if there is going to be how many bins? Countable infinite or uncountably infinite? How many bins are there going to be?
Uncountable, right?
Why?
Just the size of the bin.
Yes, that's it. It's simply because the countable union of countable sets is countable, right? And R is uncountable. So there are going to be uncountably many bins, right? That's going to become useful in a minute, right? So there are going to be uncountably many bins here.
Wait, I don't. Yeah. Could you go over the proof again? Why should there be uncountably?
Oh, definitely. Yes. Thanks for the question. So this is your entire close 0 open 1. Okay. This set you agree is uncountable, correct?
Yeah.
Okay. So since this set is uncountable, you're partitioning it into, now how many elements are there? How many elements are going to be there in each bin? In each bin, there is going to be a countably many elements.
Yes,
countably
many elements here.
Right? There's only going to be countably many elements in each bin, because if you have, say, square root of 2 plus q is going to be the bin.
Yeah, like each bin has the size of q, but q is countable.
Each bin has the size of q, right? Now, if there were countably many bins, then this entire set is going to be countable, correct? Because a countable union of countable sets is countable, and that is how you prove, in fact, that q is countable. That's one of the ways.
Yeah.
Right. So far we've agreed that if there are bins, then there exists uncountably many bins. UNCTBLY many bins. Right. Now here is where the magic is. Okay. Okay. Let's see how much we can do it without set theory. Okay. What we'll do is construct this set A. Okay. A simply pick one element
of any bin and then it just works.
Yes. Pick one element from each bin. Okay. And okay. So a question you might ask at this point is axiom of choice, plus please let's not get into that. Okay. The reason why you can do this and all that is something which is heavily debated. But so this I can do because of something called axiom of choice. Okay, let's not get anywhere close to it. Let's just agree that you can do it. Okay. So A, remember you had these uncountably many bins, and you can simply pick one element from each bin. Correct. Now this is in fact an easy claim which you can check. What you can check is that these bins are again disjoint, right? They're obviously disjoint.
0 plus 0 plus 0 plus
Yes.
0 is 1.
Fantastic.
Brilliant.
Okay, so this is something which you can check, right? This is not very difficult to see. So what this is saying is that if you translate a bin, right? Sorry, not translate a bin, but rather if you remember how you constructed this set, you took 1 point from each bin and you're taking all the rational translates of it, right? And by how you constructed, this is in fact going to be your close 0, open 1. Right, so this is something which, if it's not immediately obvious, like this is something, if it's just a cup of coffee, you can definitely get this argument, right? So this proof is not very difficult, right? But let's see, what is the consequence of this guy? What did we set out to prove? We wanted to construct a non-measurable set. What will we assume? We'll assume that A is measurable. Okay, let's see where things go wrong. Suppose A were measurable. Okay, now what is the length of close 0, open 1? It's just going to be 1. Correct? Length of close 0, open 1 is 1. Now, and this is a disjoint union. So what can I write it as? Summation R in Q, A plus R, length of A plus R. Correct? And what do we know about this measure? This measure is translation invariant. This is going to be length of A. Correct? So what do we have? What we have is 1 equals summation R in Q, length of A. Okay, my brain stops working here. So can length of A be 0? Can it be 0?
No, because like
Why?
then countable union of 0 is
Exactly.
like by our hypothesis it should be 0.
Good. So ruled out. 0 is ruled out. Can it be some positive number?
No, because like if it is say t, then 1 by t numbers
Yeah,
more
that's
than that can't be.
Correct. And infinity, we don't want it. And negative numbers, we don't want it. We're out of numbers now. We can't assign anything to length of A. We can't assign positive. We can't assign 0. We can't assign infinity. Infinity, obviously, we can't assign. We can't assign a negative number. Right? We've run into an issue here. So A is non-measurable. Okay.
Wait, I'm very sorry for doing this.
Yes. Don't be sorry at all.
I still don't get why there should be uncountably many bins. Like,
okay.
I didn't ask because you were going, and I don't want to disturb you, but can you just sort of track back in?
Oh, sure, definitely. Thanks for the question. So, what were we? Okay, why does there exist uncountably many bins, right? So, okay, so let's just take with this 0, 1. Oh, by the way, this is all what I wanted to present. So now just shoot out your question.
One more person raised it.
Yeah. Oh yeah, I'll just take this question and maybe like come back to the furious guy. Okay.
Yeah.
Okay. So see, you started with close 0, open 1, right? This you agree is uncountable, correct?
Yeah.
Okay. Just ignore the spelling. Okay. So this you agree is uncountable. Now, what did we do? We tried to partition this into bins, correct? Now, do you agree that each bin has countably many elements?
Yeah. This
okay.
Q, the size is Q. Yeah.
Yes. So each bin has size Q, right? So now I'll just prove a claim here. Maybe if let's say AI are countable sets. Okay, that means what I'm saying is, let's say each AI is countable. Okay, then this okay, so each AI is countable. That means for all I in natural numbers. Okay, then this union AI, my claim is also countable.
Yeah, I'm okay with that. Like, I'm also okay with if there were uncountably many AI, then the union would be uncountable. All that is
maybe uncountable. Not would be uncountable, maybe uncountable. Yeah.
I just want to know why there are uncountably many bins. That's
right. Okay, so consider this. So each bin, you have agreed that it is countably many, correct?
Yeah.
Now, suppose there were countably many bins.
Oh, okay. Sorry. I'm so sorry. Yeah,
okay, no problem. I'll just complete this argument. There may be others who are shy to ask, but good that you asked this. So let's say there are countably many bins. Okay, each bin has countably many points, and you take a countable union of countably many points. So what you should end up ideally is with a countable set. But what are we ending up with? We're ending up with this closed 0, open 1, which we know is uncountable. Correct? So that's one reason why. Okay. So hopefully now you're convinced that this weird looking set which I constructed is non-measurable. So in fact, there is this one thing which I read, though I'm not sure about, and I do tend to believe it, that every non-measurable set you construct will invoke axiom of choice or an equivalent statement of it. So such is the power of axiom of choice. So in fact, there are a lot of things you can do about just this axiom of choice. So there's something called Banach-Tarski paradox. So you can take a look. I think Visa has a fantastic video on it. My handwriting has not become too bad. Okay, not bad.
Yeah, it's been completely legible.
Yeah, that's good. Okay. I hope you're not being sarcastic here, but
No, I think they have gone through me writing, so everything is good.
Okay. Yeah, so I think the Furious guy, you had a question. Oh, okay, cool. Okay. I think you're doing decent in time.
Yeah. So, did we prove that if a set is measurable, then, like, did we prove that the countable thing, that if we have countably many disjoint sets which are measurable, then their length adds up?
Oh, we haven't proved it at all. We have not proved it. The proof is tricky. Proof is involved.
Okay.
Yeah.
Aniruddhan, could you just scroll up? I kind of want to see.
Sure.
Yeah.
To where you want to tell me?
Just I want to see why. Like I want to see the definition of the set, and like I kind of want to picture it a little better. That's it.
Yeah, the construction of A.
Construction of it. I'll just go through it again, maybe. So
that's okay.
It's like I can't get it in one screen, so I don't know when to stop scrolling. So you start with this.
One more thing before you continue.
Yeah.
The notes, this notes will be given to all of you, and the video will also be uploaded on the YouTube.
Then don't bother. Then just if the notes.
In that case, don't worry about it.
Oh, okay, cool. I'll just go through it. And once again, so I just found out, like, while I was talking, I found out some typos in my notes. So I'll correct them and then send it to you. Okay. And okay, so coming back to this, so I'll just give you a quick 1 minute recap of what happened in the last part. Right. You start with this closed 0, open 1. Right. Yeah. Closed 0. Yeah. Closed 0, open 1. And what you're doing is you're dividing this into partitions, right? The way you divide it into partitions is that x and y in same bin, if and only if x minus y is a rational number. Okay, so this you agreed that it will give you uncountably many partitions, correct? So now what you do is you take one element from each partition. Say one element from each bin you take, okay? So now you call this set A. The key observation which I left to you was that this disjoint union over every rational number A plus R is in fact closed 0, 1. Okay, this is a not very difficult exercise to see. That is, in some sense, these things are going to cycle around, right? So with this, what did we assign? One was the length of 0, 1, right? Which had to be the disjoint sum. Disjoint union, or the sum of sum over every rational number, length of A plus R, and by translation invariance, every rational number length of A. Now we run into a trouble. Summation over rational number, length of A, we want it to be 1, correct? This length of A can't be 0, because 0 plus 0 plus 0, or how many ever times it's going to be 0. It can be a positive number, because if you add a positive number infinitely many times, you're going to get infinite, which is, I don't think it's 1. And it can't be infinite, because it's already infinite on the right hand side is 1. And please don't get into sets with negative measures, right? So in fact, there are notions of, okay, so Rajdeep, at this point, is it clear? Rajdeep,
yeah, I was entirely okay with the whole thing. Like,
okay,
when it was done, I just kind of wanted to see what A looked like. Like, I got it, it's the quotient group and all, everything is fine. Great.
Okay, great.
What does it look like? I kind of wanted to see.
Oh, what does it look like? Okay, I have no idea. It's constructed the axiom of choice for that.
I get that why you would do this. Like, I completely get the motivation, because that's why we set up translation in the first place. All that is great. Since I have a weird brain, I just kind of want to picture everything that's happening. So that's why. But it's okay.
I don't even think it would be reasonably possible to picture it.
Maybe. Okay.
And the only reason is because it's constructed by axiom of choice. Like you're constructing you're simply saying that this set exists. I don't care how you're going to figure it out, but I'm just telling you that this exists. Just take that and go to bed. That's all what axiom of choice is saying.
Yeah.
So that's the problem with it.
Good.
It's hard to picture this.
Yeah. Okay.
Yeah. Great. Anand.
Yeah.
Yeah. No. Were you clear with this? Like, is it okay?
Yeah. Just, of course, this is mind twisting stuff, but as far as you have explained it, till I hope I've understood it.
Okay. Fantastic.
Yeah.
Nice. Okay. So now let's go to like some technical jargon. So this lambda is what is called the Lebesgue measure. So if you see someone use Lebesgue measure, now you can say that you know it, right? So this is a fantastic, like this is something like which is a really milestone thing. So this existence of Lebesgue measure, and the reason why this is so nice is that with this, Pranav is okay. So I agree that this is like very heavy. I agree, but I'll send out the notes and there'll also be the lecture video. So you can take a look, and my phone number and my email ID, everything's out on the web everywhere. So you can definitely contact me with that, right? So yeah. So coming back to what I was saying. So this notion of length, what we have, Lebesgue measure. So this is something which is exceptionally useful in defining a whole new theory of integrals, right? So with this notion of integrals. So let's just Rohan, I can go on for like about 5 minutes, right? Or
go on for whatever amount you want.
Okay, cool. So if you have a function, so I think I skipped going over, like someone had asked me to go over it at the end. So what you can do, so what you will do ideally is that, so remember I had made a statement that for any function f, there exists a sequence phi n, such that this phi n increases to f pointwise, right? That means for all x in the domain, phi n of phi n x is an increasing sequence, and limit n tends to infinity, phi n x is f of x. Right? So in fact, the way you construct it is the following. It's a rather very weird construction. So let's just say for sanity purpose again, let's just say f is continuous. Okay. So the way you construct it, you start with just the constant function. Okay. The smallest possible constant you can assign. Then you break it into two. You take the constant here, and then you take the constant here. Right? You break it further into two. You take this one.
Can't you have just done the like partitions, take the minima, partition it
yes,
further?
Ideally that will be done, yeah. That is in some sense like what you will do, but like that is that is ideally what you will do, but it gets too tricky to describe. So what I'll do is maybe I'll put up a reference for this. Maybe I'll put up a proof for why such functions phi n exist, and maybe you can take a look at that. And now I'm sure I'll lose people if I start explaining all this. So
I have a question. This is true not just for continuous functions, for all functions.
Yes. In fact, yeah, it's true for a much bigger class of functions, but I think let's.
Yeah, so I just like noticed something that your construction of phi n in general, it's a lot like how we do like a Riemann integration, like we break the domain, but here instead we broke the range into like, so yeah, okay, got it.
Yeah.
So can't you just like, if you want it strictly increasing even, can't you just do it like whatever the minima is of the range, like in the nth time you're generating, just decrease it by 1 by 2 to the end?
Yes, that is in fact exactly what you do in the construction.
Okay, cool.
Yeah.
How would you do this for something that's weird like Dirichlet's function?
What? No, I think, see, I'm not sure this holds for every possible class of functions. So this is something like which I think is for a reasonably nice class of functions. So that is something like which I will have to check if it holds for every possible function.
I was just wondering, how do you construct this for something like Dirichlet's function?
Yeah. No, so I'm not sure if this holds for every possible function. And I mean, like once again, like I'm like this axiom of choice. That is, I know that there exists such a construction, but ask me a construction, I don't know. Okay? So yeah, these things are kind of tricky. So for each individual function coming up with the fine. So in fact, there is a general procedure. I'll just open my notes. Give me a minute. So there is a general. So if you're interested in this, maybe this is something like which will take some time to prove, but I think you can definitely try it out if you're interested. Right. My handwriting is horrible. I should take another book just for
For Dirichlet's function, though, if I've understood right, Dirichlet's function is simple, right? So the function could just be, the sequence could just be Dirichlet's function for all n. Would that work?
Dirichlet is that q in one, q is
Yeah.
one q complete. Oh, okay. Right. So that will work, I think. Yes. No, but wait. So I'm searching for something which. Oh God, no, I'm not able to. I don't know where it is. No, but in the meantime, I can like just keep your questions coming. I'm just searching for the function, the definitions for phi n's which increase to phi.
So I'm like a bit confused. So what is the theorem exactly? Is the theorem for only continuous functions?
No. Which theorem are you talking about?
This theorem, that f can be like there is a sequence of phi n such that for each x, limit n tends to infinity, phi n x is equal to f of x for which function? So
okay, that is what I'm looking up. I think it is for some condition of non-negative function. I don't remember the exact criterion what it was. I'll look it up and send you the reference. I think that is a much better thing.
Okay.
Yeah, sorry about this. Like I don't remember the exact set of all functions for which this could be defined. I'll send it to you. I'll put it probably, give a reference in my notes. So as far as I remember, it is for any measurable function. But I think for measurable function, you need to okay, fine. I think yes, it will be for any measurable function. So a measurable function. Okay, so it's okay if even if you lose me, but for those interested. So if you have a metric space here, okay, let's just say R here. Okay, so if you have R with the Borel sigma algebra and to R with the Borel sigma algebra. Right. No, okay. Now that I think about it, it's true for any measurable function, right? So you call this function phi to be measurable if phi inverse of b belongs to b for all b in b. Okay, too many b's. So phi inverse of b belongs. Yeah.
What is phi?
Oh, phi is a function. So what I'm saying is that a function phi is said to be measurable if phi inverse of
phi is a function from the
R to R.
Cartesian product of R and B.
No, it's R to R. Like, oh, okay, right. So so phi is a function from R to R.
Okay.
Okay. So this B just came in because like okay. So I think a better way to say this would be if you have
it's kind of like how we define continuity in topology.
Yes, very much.
So we kind of define, instead of defining a topology, we defined I think what you mean like a Borel sigma algebra, right?
Yes. And in fact, what you said, there is a strong statement that every continuous function is measurable.
Oh, so it means measurable are like a more general class of continuous functions of sort.
Yes. So in fact, you will see that this guy. So remember that earlier function which I defined, 0 when x is rational and 1 when x is irrational. This is obviously not continuous. This is in fact measurable. Right. So I'll just go through the definition of what a measurable function is. So if you have a function from R to R, okay. So I'm just taming this definition down. So this function phi is said to be measurable if phi inverse of this any Borel set, an element of the Borel sigma algebra is called the Borel set. Phi inverse of any Borel set is in the Borel sigma algebra for all b belongs to b. Okay. So now what I confused it with is that if you have any metric space, right? So remember, so I started out with so this I'm going a little bit much more technical than what I think one can understand, but I think I'll just play along for a little bit. Let's see how things go. So if you start with any metric space, whatever that means, and if you start, if you take the Borel sigma algebra on that field, there's not a Cartesian product, just that, okay, so I'll just not go into this at all. So if you start with any metric space, say x and y are two metric spaces, right? And let bx be the Borel sigma algebra associated with x. What does that mean? On R, I started with the open intervals, correct? So instead of that, in this metric space, I'll start with open sets, right? And then I'll demand the usual things. That is, it should be countably closed under countable union and closed under complement, right? And I'll also take this Borel sigma of y, right? So this function is said to be measurable if phi inverse of b belongs to b of x for all b in B of y. This is a mouthful of a definition. What this is saying is that if you take a nice subset of y, the pullback of it, the inverse image of it is a nice subset of x. Right? So if you do this, then this in fact will show you that this is what is called a measurable function. And the statement of the theorem, if I remember correctly now, so it's okay if this doesn't make sense. So simply just take that if you have a function from R to R, it is said to be measurable if phi inverse of B belongs to B for all B in B. Okay. So now the statement of the theorem which I was talking about, I'm almost certain that this is the theorem. If you have 0 infinity, okay, infinity can be allowed, right? So what you do is, I think here you can define a sequence phi n of functions that increase to phi. Okay, and Ojas, is that okay? This I'm certain is the statement of the theorem. Almost certain.
Okay.
Yeah.
In your definition of a measurable function, that curly b. No, it's okay. You don't have to scroll. It's like right there. The last one. Yeah. So that curly b is the set of all measurable sets of R, right?
Curly b is the set of all. It's smaller than the set of all measurable sets.
Yeah. So the
L was
Borel
the
measurable.
Yes, Borel measurable is the actual right word, but let's just agree to call it Borel sets.
Yeah. So is it? Do we get into issues if we like do it L instead of B?
Yes, in L instead of B, you will get into issues, and the issues are very nice.
Oh.
So in fact, So in fact, like studying functions like this, say what is it? It's going to be from R endowed with B to R endowed with L. Right, so things like these, it's going to lead you to a mess. So right, so this also explains why I put R comma B, simply because there does not exist a unique sigma algebra associated with R. Right, there exist multiple sigma algebras associated with R, and the one I'm most concerned with is this sigma algebra B.
Right. Oh yeah, so I actually had this question before, but then I didn't want to interrupt again. Same things. There are a lot of definitions happening. I kind of want to just like pick on the motivation, because we started off by like trying to define the length of any subset of R. Then we sort of started. So like that's kind of what I wanted you to do. So track what we wanted to do and why we ended up with L or B. So you get my question, right?
Right. That's a very good question. So a quick summary. Okay, so what did we start with? We started with Riemann integrals, right? So we started with defining what, I think I'll just not try writing unless it's absolutely necessary. So what did we do in Riemann integration? In Riemann integration, we partitioned the domain space and put it into rectangles. And in each rectangle, we took the limit of this as the number of partitions goes to infinity, and claimed that if it exists and it's nice, then that's the area, right? Next, what did we come to? We said instead of partitioning the domain, why not partition the range, right? That is when we saw what are called simple functions, right? So simple functions, we started partitioning the range, right? Now, and this gave a major motivation to study lengths of subsets of R, because the inverse image of a set need not be an interval. It can be something as bad as this 1 when x is rational and 0 when x is irrational. It can be as bad as this. Right, it can be worse, but this is a bad enough example, right? So this is something what we did, and then what we did is try to define this proper notion of length. So what all did we expect from length? We wanted the length of an empty set to be 0. We wanted the length of a comma b to be b minus a, and the length of a disjoint union to be the summation of lengths. Right, this is something what we wanted, and we said this is slightly unreasonable in expecting that we want it for every possible subset of R. So let's settle to a smaller subset of R, right? Smaller subset of 2 to the R. So we settled for something called B, which contained all the useful sets we would see, right? That contained all the intervals of the form a comma b, and it contained if A, then its complement also would be there, and if AI, then union AI will also be there, correct? So we settled to the smallest class of sets which satisfy all these 3 classes, right? And this we called it to be the Borel sigma algebra, correct?
Yeah.
Now,
I'm really sorry to interrupt. So
no
we had those 3 like conditions that we liked. Like that would be the nicest conditions that we could imagine. You said that the third condition was like too strong. to like.
This one.
Yeah, this one is too strong, and it like it sort of like it's too much to expect, which is why we move to a smaller. No, I'm asking you, is that what happened?
No. We want these conditions. We want, irrespective of the sets we choose, we want these three conditions to satisfy.
Okay, so 2 to the power was too large.
Yes, what we will give up is our demand that we want it for every subset of R.
Right.
We no longer want it for every subset of R.
Right. So now we're looking for the smallest, or the largest sets that satisfy these three conditions. So
Smallest, rather. Smallest that contain intervals that have this and that have this, but largest in some sense we want to expand our scope. We don't want it to define, say, just on this phi index.
Exactly.
This is also a stupid sigma algebra.
Exactly. So shouldn't we look for the largest nice set of subsets?
No, I wouldn't go that far as saying largest, because this L is what you get will be the largest. Not will be the largest, but it is one of the largest set. Right. So maybe I'll just give a quick recap of what happened, and maybe then things will be clear. Right. So what did we set out B to be? We wanted to define this length only to these B's, right? So contained intervals, closed under complement, and closed under countable union. Right. Now what we said, we took an analyst route and just dumped the definition every possible subset of R, and then we filtered out only the reasonable sets, which gave L, right? And then we did not prove this, but Borel is a subset of Lebesgue. So this L is called the Lebesgue measurable set. This is the set of all Borel sets. This inequality inclusion is obvious. Now this is something which will require work, and this is something that we proved. Okay.
Wait, I just have a question. Is the sigma algebra determined uniquely by the measure that you're considering? Right, like for example, like could you the Lebesgue measure defines the Lebesgue sigma algebra, right? But is there like a different sort of measure for the Borel sigma algebra? Like what is the whole structure of all these sigma algebras and the measures that define them?
Okay, that's a really fantastic question. So this will go into this whole realm about what a probability density function is and what a probability distribution function is, right? So the idea is the following. See. So we'll go to something. Rohan, you can, if the file is becoming too large, you can stop the recording also. That's also fine. If
it's not loading on my device anyway.
Oh, okay. Yeah. So right. So what did we start to do? Probability density function. Right. So see, what did we want? We initially started with mu of say a comma b. Oh no. Mu of a comma b to be b minus a, correct? So this is what we wanted. Mu of a comma b, we wanted it to be b minus a, right? Now, instead of asking for this, what if I want to define a probability measure on it? That is, what if I want to define a function mu such that mu of this entire space, let's say mu of R, is equal to 1 instead of infinity, right? So this is where you can define something called a probability distribution function, right? So it satisfies the same things, right? That is, mu of the empty set is 0, mu of the whole of the real numbers is 1, and it is countably additive, right? One second. Yeah, it is countably additive in the sense that mu of the disjoint union of an is the summation of mu of an, right? Here I don't have to worry about convergence, infinity, all that. The measure of the entire space is anyways, 1. Right. So here, what else? Yeah, question.
Yeah, I think you missed this point. This mu of R is 1.
Yes.
But mu of a comma b is b minus a.
No. I was saying like we initially started with mu of a comma b equals b minus a. Instead, what I want is mu of R is 1.
Okay.
Okay. Good point.
And in this case, you can define multiple mu's, which in some sense integrate to 1 over the entire number.
In fact, that is what I'm going to tell you. So in fact, what you can do is
this makes sense a little bit.
You can define a function f, okay, associated with a mu from R to R. Now let's say R closure for some reason. Okay, R closure is including minus infinity and infinity. Right. So what you define is f mu of a to be the measure of minus infinity comma a. Where I put it for charge. Okay, so in some sense, what you're doing is that if you have a function, you take the area until that point from the very left, right? Now, So this satisfies some very nice properties. I'll just get my notes so that I don't mess up. Did I do it here or no? Okay, so this satisfies some very nice properties. That is, like, the very first property it satisfies is that I think limit a tends to infinity, f mu of a is 1, and limit a tends to minus infinity, f mu of a is minus 1. Okay, so for everything, just keep the running example as the Gaussian. Okay, some constant times e to the minus x square over 2. Right, this is how it looks. Let's keep this as the running example. So this is something what you would want, like limit f mu of a goes to 1 and minus 1 as x goes to the left and right, correct? And next other thing what you would want is that like you want all these nice properties, like it should be what is called right continuous. What I mean by right continuous is that if you have a sequence an which decreases to a, that is, if there is a here and you have a sequence an that approaches a from the right, so then what you would want is that this f mu of an should decrease, should tend to f mu of a. Decrease is natural, I think. So yeah, so the third property you want is that it is monotone. What I mean by monotone is that if a is less than b, then f mu of a is less than f mu of b. Okay, so this in some sense, like, it will make sense after you do probability theory. I'll just recap what the statements you have. You have a measure x, right? Mu from x to 0 infinity. You have this with you. Let's say r to 0 infinity. Keep the running example as c times e power minus x square by 2 and everything. Okay. So what you define is the distribution function. F mu of a defined as mu of minus infinity comma a. The a is inclusive. Okay. This will make a difference. A is inclusive. Okay. Okay. So if you define f mu, what are the properties f mu satisfies? The first property is that limit a tends to infinity, f mu of a is 1, and I'll just put a plus or minus and a plus or minus here. Wait, no, I can't do that. I'm stupid. And f mu of a as limit a tends to minus infinity is 0, not minus 1. Okay. The second property I wanted to satisfy is that if an is right, if this is right continuous, that is an decreases to a, then f mu of an decreases to f mu of a, right? And the third property I wanted to satisfy is monotonicity, right? That is, if a less than or equal to b, then f mu of a less than or equal to f mu of b, right? These are very natural properties to check. These are not difficult. So the fun part is, if you have a function f that satisfies these properties, then it is a measure.
And what are all the sets that it can measure? Like what are all the measurable sets according to these measures?
That's a beautiful question. That's a beautiful question. And that, in fact, is an answer to your previous question. So the answer to both the questions are the same, in fact. So f is, so if you have a function f that satisfies these three properties, right? So remember, with these three properties, if you sit down, you can construct 120 functions in a minute, right? So just take anything. So for example, you can take any continuous function like this. You can take any function like this, right? Or you can take a function like this, or you can simply take, say, something like this. That you can take any such function which is 0 here, 1 here, which is right continuous, which we can replace by stronger condition, which is continuous, and which is non-negative, right? So you'll get
like, suppose you have a family of Gaussians, right? You change, like, instead of x squared by 2, you make it x squared by 2 alpha, right, or something, and then you change the constant that you multiplied by, so the integral will be conserved, right?
Yes.
Do all the Gaussians measure the same set? Like, are all what are the families? Like, there's just too many things that I can ask here. I'm not sure where to start.
I'm coming to that exact very point. So now the thing is, like, with these f's, so with these f's, if you try to construct a sigma algebra such that all these things are nice. So I'm going at a lot of measure theoretic probability now. So I'll just give you references to where you can read a lot of this, right? So in some sense, what you will do is that, so if you try to construct a Lebesgue sigma algebra out of this, right? If you take this cut condition, all these, turns out that the Lebesgue sigma algebra the Lebesgue sigma algebra you construct will depend on this function f. Okay, but the Borel sigma algebra will be common to all these. Right? This Borel sigma algebra B, which is started with, is going to be common to all this. I'm speaking in a very, very loose sense here. Right? But this is something like which is why people are usually interested in Borel sigma algebra over Lebesgue sigma algebra. And I think any further on this, I think I will have to go into a lot of measure theory. So
wait, this is related to how you define the Borel sigma algebra as that intersection, right, of the family of all sets, which is such minimal in some sense, right? So okay.
Yeah, so for all these, I can send you like very decent. In fact, BV Rao's notes are like whatever I said today will be somewhere or the other in BV Rao's notes.
Notes on measure theory? Or?
Yes, notes on measure theory, probability, or something, or just this or Manjunath Krishnapur's notes. So he has a fantastic homepage. So check out his homepage. So there you'll see this one section called suggested readings for students in probability. So that's a really beautiful section where he's listed like nice books to start with at all stages. If you're a noob like me, then one place. If you're in your like intermediate space, then one book. Then if you're in an advanced thing, one book. And his final section, which I like the most, is so he goes this. So if you're a noob, then he uses better words, not noob. But if you're intermediate and if you're advanced, then final section is if you want to work with me. So yeah.
That's nice. Like you can send the list. You are sending the notes and the resources are listed there, right?
Yes. I'll put it there. I have put it there, I think already. Yeah, I've put it there.
Okay. Yeah. So yeah, is there anything else you want to add, or like any?
I think so.
Like if any further questions, I think most people here left at this point are in the batch, so they have a direct communication with you.
Yeah, so I'll just put my email ID for here, like if you want to write to me.
Also, his homepage is linked in the posts as well on the server. So you can contact him directly as well.
Yeah, this A, not a Q.
Okay, yeah, I think that is very nice. Is there anything else to add? Anyone?
Yeah, I'm being very stupid again. Just
you dare not say that again.
No, because like you've repeated this twice already. I just again for my own sanity's sake, we started off trying to define a good measure for whatever, like the reals and whatever. Then we got like 3 conditions. We realized that all of like not all subsets of R can be measured. So we started looking for a reasonable set of subsets of R, and we got the Borel sigma algebra in that. But and then we abandoned all of it, and then we defined a new measure, which was lambda star, and then we added a sanity condition on R, which was the
Kara-Theodori.
Sanity condition, and we asked that for which subsets does Kara-Theodori's condition give a reasonable set, and then we considered the set of all those subsets, and that was the Lebesgue sigma algebra.
Correct.
Then we realized that the Borel sigma algebra is actually a subset of ER.
Correct.
Okay, cool.
Fantastic. Yes, thanks for summarizing. I think.
All right. Thank you for the session. It was amazing and quite exciting.
Thanks.
Yeah, I understand that it might have been heavy for a lot of people, but that's okay. Some sessions are light, some sessions are heavy. And this was, despite being heavy, you intuited it and made a lot of sense. And I think it was quite fun.
Okay, great. Thanks. I had a great time. Like the questions were also fantastic. So I really enjoyed the talk.
Yeah. Thanks everyone for joining. I'll stop the recording. Thanks.
Thanks for joining, I should say. And thanks again, Rohan, for the invite.